All right, we are now on the last lecture, the last topic for the semester. There'll be some more lectures, video lectures after this, but those will all be review, especially going over practice final exam problems to get you ready for the final. So the last topic is the theory of rate constants. I say here in the text for this section that the theory of rate constants is kind of not been successful, even though people have been working on it for more than 100 years. And the reason for that is that it's extremely complicated. It's extremely quantum mechanical. It involves bond breaking. And it doesn't just involve finding, a few quantum mechanical facts like the wave functions or the eigenstates of the Hamiltonian or anything like that. It involves time-dependent behavior. It involves deep understanding and computation on large parts of the space available to the quantum behavior of molecules, and that's just really difficult to do. People have been working on that with the biggest computers available for a long time, and still only a very small number of very simple reactions can have their rates predicted quantitatively, reliably from first principles. However, having said that, there are a number of semi-quantitative theories and what you might call phenomenological theories that are still very, very useful, and we'll talk about one of them today. And in fact, all of our understanding of the kinds of things that give rise or that control the value of a rate constant, and therefore the speed at which a chemical reaction takes place, are due to these simpler theories. The very simplest of them all is Arrhenius theory. Now let me say from the beginning that Arrhenius theory isn't really rigorous. It's an approximation, and it doesn't always get followed by every chemical reaction. You have to kind of prove, if you're going to do this in any research setting or any setting where the reaction is not very well known, you got to kind of prove that it's Arrhenius before you start using the Arrhenius theory. There are better theories out there that aren't a whole lot more complicated than Arrhenius, and sometimes people use those rather than Arrhenius for that reason. But that said, probably Arrhenius, it's the oldest and probably still the most widely used of all the rate constant theories out there. So let's look at the Arrhenius law here, the Arrhenius expression. Here it is. It's pretty simple. It says that the rate constant, and this holds for any type of rate constant, first order, second order, 10th order, whatever, is equal to a constant called A, and that is called the pre-exponential factor, times a Boltzmann factor, really, a probability factor, whose value is controlled by this energy called the activation energy. There's a qualitative picture that goes with this and that helps interpret these two quantities, the pre-exponential factor and the activation energy, and we'll talk about that in a minute. But for the moment, those are the parameters that go into the Arrhenius equation. A technical point before we move on is that this exponential factor out here doesn't have any units, obviously, and that means that the units on K have to match the units on A. So for a second order rate constant, for example, the units are molar to the -1 seconds to the -1. That means the units of A have to also be molar to the -1 seconds to the -1 for a second order rate constant. For a first order, though, the units are seconds to the -1, and that means that the units of A have to match that in that case also. So the units on A vary depending on the type of reaction that you're working on, the same as the units for K do. All right, so that is the Arrhenius expression. What's this qualitative picture that goes with it? I imagine many of you have seen this kind of thing discussed before, but it doesn't hurt to review. And maybe somebody hasn't seen it already, but it goes with this reaction energy diagram, as it's called, at least in the freshman textbooks. So what the reaction energy diagram has is energy on this axis, on the y-axis, and something called a reaction coordinate on the x-axis. This reaction coordinate is essentially never well defined, well, at least outside of research settings anyway. In the literature, you'll see the reaction coordinate actually defined. But that's pretty rare. Most of the time in most settings, nobody ever talks about what this really is, but what it really means is that you have two sides to the diagram. One side that represents the reactants in the chemical reaction, the other side that represents the products, and by moving from left to right, you're going from the reactants to the products, and as you do that, the energy of the system is changing, is going up on the left-hand side and coming down on the right-hand side. And so there's an energy barrier. The system has to have, the reactants have to have a certain amount of energy in order to get from the reactant side of the diagram to the product side of the diagram and therefore create the products. And that energy barrier, that need, that requirement that a certain amount of energy has to be acquired, you know, to break bonds or partially break bonds anyway, is where this exponential factor comes from in the Arrhenius form. That e to the minus EA over RT is a Boltzmann factor, right? It's calculating the probability that the system started with this much energy and ended up with that much energy just by gathering energy from the surroundings, from fluctuations, from collisions and stuff like that. And so that's a Boltzmann probability. And the other term in the Arrhenius form is called a frequency factor. It's basically an attempt frequency. Let me go down here. I have a diagram down here, but the picture is this, that the reactants here are always fluctuating. They're colliding, they're vibrating, they're rotating, they're hitting each other, they're hitting the walls. And in the course of that, they gain energy, they lose energy to the surroundings. And every time they do that, it's effectively an attempt to break some bonds or to form some bonds or to rearrange the molecule, whatever kind of reaction is taking place. Every one of those fluctuations represents at least an attempt to carry out the chemical reaction in question. And the only question then is, well, do they have enough energy to actually do that, to actually carry out the attempt? And the answer to that is, well, there's a probability for that. It's e to the minus EA over RT. So A is the rate or frequency at which attempts are being made to cross the barrier, and e to the minus EA over RT is the probability that that attempt was successful. That's the sort of qualitative, at least, understanding of where the Arrhenius form comes from. All right, once you cross the barrier, it's all downhill. You don't need energy anymore coming down, and eventually you get over to the far right-hand side where the products have occurred. On the other hand, this diagram doesn't just describe the forward reaction. If you started over on this side with the products, you could also in principle go the other way. You can go backwards too. So the reaction energy diagram actually describes both the forward and the backward reaction. It therefore describes both the forward rate constant and the backward rate constant, or reverse rate constant. And that means there's really four quantities describing a given elementary reaction. There's an attempt frequency for the forward reaction and a barrier or activation energy for the forward reaction, and there's also an attempt frequency and a reaction barrier for the reverse reaction. And notice that if the energy goes downhill and going from reactants over to products here, notice that the energy on this side is lower than the energy on this side. So energy is going downhill, you're losing energy, it's an exergonic reaction. Then the barrier on the reactant side will be smaller, and that means this exponential factor will be bigger going forward than if you're trying to go backwards, right? The barrier on this side is bigger, and this barrier factor this Boltzmann factor will therefore be smaller for the backwards reaction than for the forwards reaction. On the other hand, it's perfectly possible to write a chemical reaction, an elementary reaction, where everything is reversed. You can start low and end up high, and then this would be the forward reaction, this one would be the backward reaction. And in that case, the Boltzmann factor for the backward reaction would actually be greater than the Boltzmann factor for the forward reaction. There's no rule that says that you have to start at high energy and end up at low energy. You can do it the other way around. All right, so that's the Arrhenius theory in a nutshell. Let's see if there's anything else I should say before we move on. I think that's all of it. There are many other things to say about this theory, but we are running short of time, and a lot of those things would take some time to explain and also are kind of secondary. This is really the primary stuff anyway. So, all right. That's the picture. I guess the next thing to say before we move on is this calculation here. The question is, okay, if there's an attempt frequency that's trying to cross the barrier, and then there's a success probability that's measuring or taking into account the probability of getting enough energy to cross the barrier, how big are those two numbers? Well, a typical reaction energy barrier height is about 50 kilojoules per mole. And that means that we can plug that in. If that's EA, we can plug that in at room temperature, where KT or RT is about 2.5 kilojoules per mole. That means that the Boltzmann factor, or the probability success factor, is about e to the minus 20th, which is about 2 times 10 to the minus 9th. So what that means is that even though the system is making attempts to cross the barrier very rapidly, many, many times per second, 10 to the 10th times per second, let's say, the success of any one of those attempts the success probability is really low. It's 1 in a billion, or thereabouts. And so that's the story behind the Arrhenius theory, or the Arrhenius picture of how a chemical reaction takes place. There's a very fast attempt frequency due to microscopic fluctuations, and then there's a very low success probability, about 1 in a billion. But even though that's very low, there are so many attempts that eventually the reaction actually does take place, and it takes place at some appreciable rate usually. All right, so a typical value for the pre-exponential factor, I don't have it written down here, but pre-exponential factor A is typically on the order of 10 to the 9th itself, 10 to the plus 9 now, or even 10 to the 10, or 10 to the 7. I mean, there's a fairly big range for the values of A. It depends on the reaction a lot. But they're big enough so that they can largely compensate for the very low success probability for each attempt. All right. There is perhaps the most useful thing about the Arrhenius theory, the thing that it explains. I mean, this picture up above is very valuable in its own right. But the quantitative thing that the Arrhenius theory allows us to do is account for the temperature dependence of the rate constant. If you heat up a chemical reaction, the equilibrium constant that we talked about earlier may go up or may go down. It depends on the sign of the delta H for the reaction. If the delta H of reaction is negative, in other words, an exothermic reaction, then the equilibrium constant actually goes down when you raise the temperature. If delta H of R for reaction is greater than 0, an endothermic reaction, then the equilibrium constant goes up. But rate constants always go up. And the reason is, you can see from the reaction energy diagram picture up here, it's because when you're raising the temperature, you're raising the probability of having enough energy. You're raising the amount of thermal energy available, and therefore you're raising the probability of having enough energy to cross the barrier. And so you always are raising the rate constant when you raise the temperature, and that effect is accounted for by the exponential factor in the Arrhenius theory. As a practical matter, we can therefore do the following. Let's suppose we want to find out what A and EA are. Well, especially let's suppose for the moment that we want to find out what the activation energy is. How can we do it? But we can measure the rate constant at 2 different temperatures. Let's suppose we do that. We measure it at temperature T2, we measure it at temperature T1. If we take the ratio of those two measured rate constants and do a little bit of algebra, we get this form for the Arrhenius law. I call it the two-point form for the Arrhenius law, which says that the ratio of the rate constant at two different temperatures is equal to e to the minus EA over R times the difference in 1 over the temperature. Or if you take the log of both sides, the log of the ratio of the two rate constants is equal to minus EA over R times 1 over T2 times 1 over T minus 1 over T1. That's a useful form. It allows you to calculate, if you know these rate constants at two different temperatures, it allows you to calculate this EA. But there's a better way for most applications, for most sort of research setting kinds of applications, and that's the following. Let's suppose we just take the natural logarithm of both sides of the Arrhenius law. Then we get the following. The log of the rate constant as a function of temperature is equal to the log of the pre-exponential factor minus EA over R times 1 over T. If we compare that to the equation for a straight line, if we call the log of T of K of T to be Y, we call X to be 1 over T, then minus EA over R is the slope, and the log of A is the intercept, and that says that if we plot the logarithm of a measured K value versus 1 over the temperature, we should get a straight line, and the slope of that straight line should be minus EA over R. So by multiplying the slope by minus R, we can get the energy of activation, and the intercept should be log of A. We can get the intercept. We can get log of A. That means by looking at the intercept of such an Arrhenius plot. But the intercept often has a lot of error associated with it, so that's probably not the best way to do it. Anyway, it can be done, but it usually isn't done that way. There was one other thing I needed to say here. What was that? Well, maybe I'll think about it further down. Oh, yes, I remember what it is now. I say it down here. The fact that log of A versus 1 over T gives a straight line is only true if the Arrhenius law is valid. If the Arrhenius law isn't the right law, then we'll get some kind of curve or messy plot from a log A versus 1 over T plot. So getting a straight line is strong evidence, proof for most purposes, that the Arrhenius law is good. And that's very important because the Arrhenius law is an approximation. There are reactions that don't obey it very well, and all the more rigorous theories go to show that the Arrhenius law really shouldn't be obeyed. It's just only approximately obeyed. And so proving that the Arrhenius law is actually good is an important step in any analysis of this kind. Okay, that is the Arrhenius law in a nutshell. Now let's do a fairly long and complicated example, exercising all these things in at least a sort of minimal way. So first of all, let's consider some abstract chemical reaction. A plus B goes to C, reversible. So there's a K1 and a K minus 1. And that means that there's really two reactions present, of course. There's A plus B goes to C with rate constant K1, and C goes to A plus B with rate constant K minus 1. This K1 is our K forward, our forward rate constant, and this K minus 1 is our K reverse, our reverse rate constant. Notice also that since these are both elementary reactions, you can tell just by the fact that there's two products here that this is a second order reaction. But the reverse rate constant is in fact a first order reaction. And that means that K1 has units of molar to the minus 1 seconds to the minus 1. K minus 1 has units of seconds to the minus 1. The ratio of those two has units then, therefore, of molar to the minus 1, not unitless, but that means that we're using a 1 molar standard state. So when we calculate equilibrium constants using K1 over K minus 1, using the, what's it called, the detailed balance theorem or principle, that we're going to get an equilibrium constant for 1 molar standard state. And that's important for understanding what numbers we're getting. All right, here's the questions we're going to try to answer. Do these reactions obey the Arrhenius equation? We have to look at the data to tell that, but that's one question we can answer. Find all the Arrhenius parameters for both the forward reaction and the backwards reaction. And then also find some thermodynamic parameters, the delta H of reaction and the delta S of reaction. We can get all that information from kinetic data because there's a close connection between kinetics and thermodynamics after all. Here's our actual data in a nice table. The temperature at which all the measurements were made, the rate constant that was made at each temperature, notice the units again, the backwards rate constant at each temperature, and then the ratio of those two rate constants to give us the equilibrium constant. And of course, it's this way in which the equilibrium constant is changing with temperature that's going to tell us about these thermodynamic parameters that were asked for up at the top. A couple of points before we actually start doing complicated things. The first is, let's look at these actual numbers. Notice that if I change the temperature by 10 degrees, the rate of reaction about doubles. And then if I change it by another 10 degrees, it about doubles again. And if I change it by still another 10 degrees, it about doubles again. That's the rule of thumb that many experimentalists go by. If you change the temperature of a reaction by about 10 degrees, it about doubles the rate. Now, that's only true if your energy of activation is about 50 kilojoules per mole. If it's much bigger than that, then you'll get a bigger change for every 10 degree step. If it's much smaller than that, you get a smaller change. But a 50 kilojoule per mole activation barrier is probably the most common sort of range for activation barriers for chemical reactions. So that's a good rule of thumb. If you don't know anything else about the reaction, you can give a decent guess that the rate will change by a factor of 2 for every 10 degree change in temperature. And a good part of the time you'll be at least roughly right, and that's useful. The other thing to point out is that over in this column, the equilibrium constant is actually decreasing as the temperature rises. What does that mean? Well, I pointed that out above. It means that delta H for reaction must be less than 0. Just by the mere fact that the equilibrium constant is going down as temperature rises tells us that it's an exothermic reaction. So we already know that, and knowing that this is already kind of doubling, we already know that this energy of activation must be in the neighborhood of 50 kilojoules per mole as well. So we actually have a pretty good load of qualitative information just by examining the qualitative features of the data here, and that's a useful thing to be able to do. All right, in order to we're going to want to make an Arrhenius plot like this one up here. Actually, we're going to have to make 3 different plots. We're going to make an Arrhenius plot for the forward reaction, an Arrhenius plot for the reverse reaction in order to get the energy of activation in the forward direction, the energy of activation in the reverse direction. And then we're going to make a Van 't Hoff plot down here in order to get the delta H of reaction also. So we're going to make 3 different plots, but they're all almost identical to each other. For the Arrhenius plot, we need 1 over temperature for the x-axis. We need natural logarithm of K1 for the y-axis for the forward direction. And we need natural log of K reverse, K minus 1, for the Arrhenius plot for the reverse direction. And then we're going to need log of the equilibrium constant for the Van 't Hoff plot in order to get delta H of reaction. So we now have all those numbers here. I computed those just by taking logs and 1 over t here from the data up above. And the rest is now just calculations. First of all, we've got to make a plot. And okay, this is a pretty complicated plot. Let me blow it up so it's a little easier to see. Actually, I don't think I'm going to need this pane over here, so I can make it a lot bigger, and we can still see everything else at the same time. So there's really 3 plots here. Let me choose a weird color so you can see where I'm marking. First of all, this axis, the blue color, is where I'm plotting the logarithm of the forward rate constant versus, notice, 1 over t down here. And notice that the range or scale for this x-axis here is set by the range or scale of 1 over t values that come from the data. And notice that it's a pretty narrow range. It goes from 3.333 times 10 to the minus 3 down to 3.03 times 10 to the minus 3. So it's only a pretty narrow percent range in the change in 1 over t. That's typical. You normally can't change the range of temperature very much because things start boiling or freezing if you do. And so a range like this where you've changed the overall temperature by, in this case, 30 degrees Kelvin, is a pretty good, pretty typical range, but that doesn't give you a very big range in 1 over t, and so this x-axis has a pretty narrow range also. Then the range on the y-axis here for the k forward plot is also chosen by the range of values that we got for the logarithm of the forward rate constant, and there's a similar range for the reverse rate constant and for the log of the equilibrium constants. And that gives rise, if I then plot this column versus this column, I get this blue curve here, and the slope of that blue curve, which is what we want, right, is minus 6,017. Let's look at how we use that before we move on to the other curves. So the slope was minus 6,017. That's equal to minus EA forward divided by R. So multiplying by minus R on both sides, the EA forward is R times the slope, which is 8.314, minus 8.314 times minus 6.017. And that gives an EA of 50,000 or 50 kilojoules per mole. It's exactly the sort of typical number that you get for most chemical reactions. One sort of small check you can tell yourself as you're doing these kinds of problems is that an energy of activation is always positive. EA is never negative. So if you get a negative value here, you did something wrong somewhere. A negative value here would correspond to a curve with a positive slope over here. And so if you get a positive slope when you plot the data, you're doing something wrong. Right away you know. All right, that's it for, that's the EA in the forward direction. Now these green values over here are the scale on the y-axis here for the reverse direction. That gives rise to a linear plot. Notice that these are very linear. Of course, this is all calculated data, so of course it's linear. But the fact that it's linear proves that these reactions obey the Arrhenius law, and therefore Arrhenius is good and all this is good. Anyway, the green line then is for the reverse reaction. That has a slope of minus 9.033, and going through the same calculations gives us a backwards energy of activation of about 75 kilojoules per mole. Finally, we're plotting the log of the equilibrium constant versus 1 over t for the Van 't Hoff plot. That gives us a positive slope, right? Because, in fact, when we do all the calculations, I mean, it's the same calculation, really. Oh, sorry, that's the wrong thing. This is the one we brought down here. The slope for a Van 't Hoff plot is minus delta H of reaction over R. Therefore, delta H of reaction is minus R times the slope. So it's the same calculation as for the activation energies here. It's just that it's a different quantity we're calculating. And multiplying that all out, the slope is 3,000 plus 3,020, gives us a delta H of reaction of about minus 25 kilojoules per mole, which is in agreement with what we saw in the raw data, right? That the equilibrium constant was going down as temperature went up, therefore we should have an exothermic reaction, therefore delta H should be negative. Okay, that gives us the energies, the two activation energies in both directions and the delta H. Now we want the pre-exponential factors. This is not a very good way to get the pre-exponential factor. It doesn't make use of the full data, but for our purposes it will do. Doing this more properly is a lot of work, and I don't want to mess with it, especially at the very tail end of the semester here. But, so, in that case, to calculate AF, all we have to do, we now know the activation energy for the forward direction, so all we have to do is divide, and we know KF, right, at a whole bunch of different temperatures, so we pick one temperature, T equals 300 here is what I chose, where we know KF, and we know temperature now, and then you just divide these two sides to get that the frequency factor is then KF divided by this exponential factor. Again, yes, I chose 300 as the temperature. And then just doing the calculator work gives an A value about 3 times 10 to the 10th. And notice the units, molar to the -1, seconds to the -1. Those units, again, have to match the units of the rate constant itself. And they naturally will. This 59 has units of molar to the -1, seconds to the -1. So if you just keep track of what the calculation is telling you, you'll get the right units. All right, same thing now for the reverse reaction. Gives 3.1 times 10 to the 11th seconds to the -1 for the frequency factor in reverse. And now we want to get the delta S of reaction. We know that the delta G of reaction, which is minus RT log of KEQ, at some temperature, let's say T equals 300, again we know the equilibrium constants at a bunch of temperatures, let's just pick one temperature. Then we can calculate delta G at that temperature, and then we can solve for delta S. That gives delta S is delta H of reaction, which we now have, right? We calculated that from the Van Hoff plot, minus delta G at one temperature, divided by that temperature. And now if I plug in the definition of delta G here, I can simplify things a little bit, so it becomes delta H of reaction over temperature plus R times the logarithm of the equilibrium constant, in this case at 300 Kelvin. And plugging in all those numbers gives a delta S of reaction of minus 19.4 joules per K. And with that, all those pink marks, we are done with new material for the semester. After this, all new videos will be going over the practice final and other things.